I want to introduce the first speaker of the night, Payam. Payam, please come up. Yeah. Do you need to set up or anything?
It's there.
Oh, okay, great. All right. So as he's getting set up, I'm just going to introduce him. Payam is a seasoned expert in machine learning and AI, and he has a PhD in machine learning and over a decade of industry experience. More recently, he's been working on leveraging generative AI capabilities into enterprise readiness solutions. So his talk tonight will be on enhancing the knowledge graph within generative AI features in Google Cloud Vertex AI.
All right. Thanks, Catherine. Good evening, everyone. I'm super excited to be here tonight to share some thoughts on pretty much like enhancing generative AI. So pretty much how we'll be able to enrich the backbone of generative AI in specific of generative AI. My meaning is around text, not necessarily on some other component like video or images, mainly on text. How they be able to enrich the backbone mainly using knowledge graph. Just wait a second here. So what is graph? Definitely I'm not talking about that type of graph. So I'm more about the connected graph, which is a little bit like a different representation of day-to-day data that we can see everywhere. Graph is pretty old. Back in pretty much like a century ago by Leonard Euler. Those who have like mathematic backgrounds knows that graph by Euler pretty much really advanced kind of like a field of mathematics, and it's sort of like a different representations of tabular data or like a relational data. Oh, by the way, there is a little bit of the debate around people that are working with graph and non-graph. So we refer to relational, like a relational database. So pretty much relational means graph. So I personally prefer to say tabular rather than relational. Maybe before getting into the main topic, which is around generative AI or machine learning in general, have a very quick, like a crash course on graph. Maybe pretty much, I'm pretty sure most of you know about a graph, but it's good to have like a little bit of a refresh around that. Graph pretty much consists of mainly 3 elements. We can say node, or pretty much like a vertices, is basic building block of any graph. Pretty much is, wherever we store the informations, and all the information we refer to as a properties. So if you have a properties, we can bundle the properties under a label, and that label is node. But that node could have multiple labels. So this could be a person, but at the same time can be pretty much belong to a geographic region as well. Another component, it would be around relationship or edges. So now pretty much connecting 2 labels, 2 sets of information through a sets of the relationship. That's mainly is a representation of the basic graph. For comparison, or for better kind of like a understanding, maybe, again, that's relational. I don't like to be relations to tabular, but for example, in a relational database, we have rows. We can say that sort of is nodes. There's a slight difference, but anything that we refer as a nodes, with a different dimension, we can say nodes, because they're not necessarily a one-to-one relationship. When referring to the table around the joins, mainly it's a relationship. So pretty much we're joining sets of these rows to another rows in different tables, means joining relationship to nodes. And pretty much like a table name could be labels. And in general, the columns representative the relationships. That's pretty much is a different interpretation of tabular form. Now, just a little bit of the quiz. This is pretty much a metro, kind of like a metro map. We'll be able to model this data into tabular form in a relational database. Definitely we'll be able. But if you think about that, that would be a really messy table, or we need to define lots of number of tables, and we won't have a specific schema. A schema would be changed if we, for example, getting a new lines over here. The reason is, say you want to say that, for example, for, I don't know, over the city park, all the way to golf course here, what are the number of routes we can find? If you want to find this one through relational table, think about it, how many join we need to set. What are the form of the tables? But literally graph is exactly as this. Graph database literally the same as this. We just need to define each station as a node. So how many stations we have? Roughly, I don't know, 200 nodes with the relationship, and the properties could be, I don't know, this goes to this with the red properties, and the red properties represent a line. So literally graph really help when we're going to define a relationship that connected, like pretty much like a connection of the people in social media, or even the internet browsing. Now, a little bit like, let's talk about knowledge graph, but it would be better that rather than, again, similar to the previous section, which is more like education part of the lecture, we straight away go for example in machine learning. Graph representation for machine learning. I'm starting with a use case, because that would be very easier to digest. One of the most important, or like a well-known use cases of graph is around fraud detection. But before I'm going through this, who heard about Panama paper? Yeah, right. So Panama paper is pretty much like back, I'm not really sure when, but I think it's about like 8 or 9 years ago. It's like a big scandal that happened around, you know, a lot of different companies and famous people, politicians, celebrities, for money laundering, hiding the tax and all of this stuff. That some journalists, I think, I'm not sure based on Hong Kong or not, but they used to live in Hong Kong at that time, found all of those documents. And companies like Neo4j and Graph, they'd be able to analyze all of those documents and find a relationship of document owners to be able to find the source of scandal. So really finding a pattern that source into a activity, that's where the graph is really powerful. And mainly that activity could be fraud, or could be something else, but mainly people really care or really looking for find that sort of like activities. Things about like credit scoring or credit card companies, or all of those companies are trying to find any fraudulent transactions. A very common approach is to build a classifier. Could be a very binary classifications, whether this is a fraudulent activity or transaction or not. I believe that if a data scientist wants to build such a model, is going to look at the individual features based on the payment or users, or could be a different type of attributes, and build a classifier. XGBoost or decision trees, random forest, neural net, any type of model, and kind of like be able to build model based on features like amount of transactions, date, origin, destinations, target, and resulting of the transactions. These sort of like features. But there's a lot missing through this, because in that case, again, back to the definition of relation, the features through this would be on the row level. Each row represents a transaction. And by the nature, they're looking at every single transaction. And their interaction and relationship between the multi-transaction is missing through this sort of the practice. That's why graph, it comes into the game, and try to build a model, a machine learning classifier model based on a graph. Now think about a graph like this, and suppose that all of those dots is represented transactions, and the red one is a fraudulent transaction. Literally, the machine learning algorithm will be able to identify a nodes and the relationship that's a little bit different than majority of like a underlying distribution of non-fraudulent nodes. That's where that in a graph you'll be able to find out. But I want to specifically talk about some of very famous or common algorithm in graph. And again, specifically, I may refer to technology like a Neo4j, as I'm from Neo4j, and talk about the graph data science technology in Neo4j. There are a few algorithms that for identification of the fraud you'll be able to use, like weakly connected component, that to find disjoint communities, or they call like a community detections, to find a community. And what does a community means is like a clustering in machine learning. You find a bunch of nodes, a relationship that acts differently. Or using algorithm like Levin methods. So pretty much is like a centrality. Find a sort of a transaction that as a center and relationship, and every in and out, out and in and out from and to that the transaction behave a little bit differently. Or PageRank, the top transactions or bottom transactions that again act differently. But the problem with this stuff is based on requirement is known exactly the patterns. So we need to know the patterns of fraudulent, which is unknown in the majority of the cases. And there is a technology in graph they call it graph embedding. Graph embedding, the reason I'm saying this because that literally would be a segue through a large language models and the text, because kind of there's a significant relationship between this sort of technique all the way in the text when you go through the text. That techniques of the graph embedding literally is a very kind of like a interesting techniques that boil down the complex topological informations of a graph into a very fixed length vector. For those who kind of familiar with a vector database, who's familiar with the vector database? It's a sort of a database that regarding look at the informations as numbers or as a string or as timestamp, they're looking at is like a token, and that token is like a encrypted version of a series of informations. Now think about a graph, nodes of the transactions, relationship, amount of money, when, paid to who, how much, who withdraw that. All of those relationships can be defined and encoded through a token. And that would be a vector. It's better to say tensor. There is a difference between tensor and vector. Tensor is a multidimensional vector. So we'll be able to say as a tensor vector. So now, graph embedding literally find all of those relationships as a vector. Once find as a vector, pretty much any other new information that coming, again, convert it to the vector. If those vectors are close enough to each other, it means that those are the similar. So this is the way that we'll be able to identify fraud based on the case that already we know fraud. So in your graph database, you cannot label transactions of fraud, fraud, non-fraud, 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 fraud. So a new information will coming, convert it, embedding to a vector, and compare those vectors in terms of length. Those are closer to each other, means similar to each other. That's pretty much the things that graph embedding does. Now, there's a little bit of the code. Of course, we're not going through the code. This is like a piece of code that in Cypher. Cypher is query language for graph. In Cypher, we'll be able to run this, and it converts that graph or that subgraph into a vector. Or it's better to say that embedding it through encoder. Once we encoded the graph dynamics, we'll be able to use like a technology like Vertex AI, which is part of the Google Cloud. So you'll be able to dump the information into a data frame like a Panda or CSV into a Google storage. So now you have a data in the graph data form, convert it to a tabular form as a vector, not as a data. Vertex AI, put it into a Google storage. That GS stands for Google storage. sorry. Once go to the Google storage, now be able to call a model, a predictor model again into the Google Cloud to be able to understand all of those relationships. And you'll be able to deploy it as endpoint. And Google gives you that as an endpoint. Now, in future, you get a new set of information to graph. You'll be able to call that endpoint in real time, and in real time convert the new information to vector, push it through the endpoint, and it predicts whether it's a fraud or not. This is pretty much one of the main use cases of graph for machine learning. Now, in this section, I'm talking about generative AI, and again, back why I talk about this, like a vector and machine learning and the fraud detections. Just remember that vector database and tokenizations. This is very standard way that nowadays it's pretty much everywhere for generative AI. For those who have experience with ChatGPT or any other large language models. But by the way, it's very interesting as a fun fact. ChatGPT, the underlying technology is GPT. So who knows GPT stands for? No, GPT. Perfect, yeah. Generative pre-trained transformer. So transformer is pretty much sets of transformers. So sets of the mathematical functions that transform a string into a vector. Back to that example. So you have, for example, say, this is GDG Sydney meetup. So all of those words as a noun, adjective, verbs, are going to convert to token as a vector. So that transformers, that function that convert this text to token, that's transformers. So now you have millions of documents for like, forget the name, Wikipedia. If you have enough GPU power to transform all of the content of the Wikipedia to the graph database, you have a pre-trained transformers. And if you build a generative function on top, that if you ask something, convert it to a vector, look at your vector, and generate something, you have a GPT. So GPT, the first GPT built, I think, back into 12 years ago, or 13 years ago. But because of lack of easy access to GPU, it was really hard for everyone to get access. And now, because of the GPU's access, it's the technology back to 10 years ago. But because of GPU, now everyone can get access. So standard is, you have a questions, smart search is simple, is a lookup function. You look at the text, but again, there is a transformer. In all of generative AI, there is no search through the text. Always search through the vector, through a token of a text. You search it, pass it through one of those transformers, large language models, generates outcome, and give it to you. The problem here is that part is very generic. You don't know what to look up. You need to pretty much like augment this part with the domain-specific informations. That's why we need a knowledge base. Knowledge base is where that, when you ask questions, it knows where to look up. You can have a Wikipedia down there, right, to look up in a Wikipedia. But the question is, Wikipedia is not peer-reviewed. I may not necessarily is a domain specific. Maybe you want to ask a question about the compliance that related to ASIC or APRA. So you need information about the ASIC or APRA. Or you need to have like a question, ask a question about TensorFlow. You need to have a documentation about the TensorFlow in Google as a knowledge base. This part in knowledge base, the technology underlying is based on a series of the documents, PDF, text, file, whatever. These are as like an example as a format, not necessarily this. Any sort of information that you have a text as your documentations, they're going through the processes, make them as a chunk, and produce a vector representation of a text, put it in the vector database, and you have a vector database underlying as a knowledge base, and then when you ask a questions, your question convert to a vector. Look at this to find out which of the vector in this database is close enough to a vector that you're asking. And literally the vector is distance, is like a distance, like a Euclidean distance between two vectors. And in fact, the one with the kind of like the minimum distance would be the one that most likelihood, the most reliable. Not reliable. Reliable is not a good term. It's the most relevant. But what is the problem with this? Simple vector similarity search might not be sufficient. You're asking a question. Maybe your questions, it's not, the answer is not in one document or in one chunk of text. Could be in a multiple, or no, it's similar like a human. Maybe you need to read 2 documents, understand both, connect them together, and then the answer is there. For example, you may read something about mathematics, something about physics, and something about chemistry, and you come up with your own interpretations. And if someone asks a question, you answer it based on your interpretation, not the exact text through this. So that's why we need graph. And a knowledge graph as a condensed information storage. This is an example. Say there are lots of documents, like articles. In traditional form, you're looking as information through this. And if this chunk as a vector close to your questions, okay, your answer would be around this, whatever is there. But think about that. We have a graph representation of documents. All right. These are, for example, the name of the authors, the people who wrote these articles. Also, we know that these are funded maybe different companies, and they work for this company. Also, they publish different articles, and they kind of like even these articles mention name of this company, or this article mentioned this guy that worked with this. So literally, you come up with a lot more connected information that your lookup or smart search, not looking for a piece of chunk, is go through all of those connections and combine all of those informations. And that's why we put knowledge graph over there. And this smart search or lookup using a Cypher query, again, I'm emphasizing the Cypher is open source query language. By this, the reason I bring it here because of Neo4j and the kind of like a query language. And this is pretty much the standards, because I think soon, similar to SQL, we're going to have GQL, graph query language, but graph query language is still open source. It's not something registered, but I believe in 2 years, become registered like SQL. So pretty much through the SQL, go through the knowledge, and instead of find that chunk of text, it gives you way more connected text. That's why it's enhanced. Now, again, there is a little bit of limitation with this. And that limitation is about domain-specific knowledge. Some of the questions you may ask, but again, in the next couple of slides, I'm going to do an example that has become more tangible. But maybe you ask a questions. That question convert to a vector. And that vector is not close to none of things here. But in reality, there is. But those 2 vectors are very different, and I'll tell you why. So we need another layer of augmentation on top of this that kind of like standardize all the vectors from the questions and the knowledge. Very simple example. For example, I'm asked something in a different language, like French over there. And if all of the information is in English, none of those vectors are close enough. But definitely the answer is there. But the vectors are different. We need a standard way. So one of the standard ways is the same language, obviously, unless you need to have a translator between. Now, there is a concept we call it open instruct, prompt learning. We need a mechanism that whatever is a prompt we're asking, and make it standardized based on your knowledge graph. And that would be a technology like a Vertex AI in Google. By the way, because of the constraints of time, I'm a little bit like moving fast through this because I want to go through the examples. Vertex AI in Google, this is free. Literally everyone now can have a hands-on on this. It has a kind of like a features called Generative AI Studio. If you go to like a Google Cloud in the Vertex AI part of the language, you'll be able to create your own prompt. And once you create your own prompt, it allows you to write some questions and answer them based on your knowledge. I'm not going through all of those parameters. These are highly related to the machine learning, how you'll be able to configure different parameters. But in example, in the next couple of slides, I'm explaining how this prompt works. So once you have knowledge graph in place, you have the open instruct prompt in place. Some of the like a open source or off the shelf, or whatever you call it, as a large language model, like Palm 2, Bard AI by Google, all can be sit here. ChatGPT or GPT is one of them, but it's not open source. Llama by Meta, Llama 2 just recently came. DALL-E by Databricks. There are quite a few, so every day a new one comes in place. Again, there are a lot of questions around the peer-reviewed documentation backend, so that's why reliability or accuracy is a little bit of the questions. But there is an interesting term in a large language model. No one uses accuracy. They're calling hallucination. So it's an interesting term. I want to give you like a use case as an example. And through this example, I'll kind of like explain all of those prompts and things. Cyber attack path analysis. I just put this one here because this requires a little bit of the prerequisite before I'm going through this. Has anyone heard about MITRE attack? Perfect. So MITRE attack is pretty much a framework at the enterprise level that kind of like explain how an attack happened from all the way initial access to pretty much a screwed exfiltration and impact. There are lots of like a technique and tactics so I'm not definitely going through each. There is the page for this, MITRE attack. Literally you'll be able to see, for example, in initial access, if someone sends you an email through the phishing, there's an attachment, you click on this link, and then go through the next, you give there's an execution, happen after that, all the way through discovery, collection some of the files, exfiltration, and impact. So it's a very interesting framework that shows all the possibility of attack path from the access to impact. The reason I'm saying this is in case of cybersecurity, you will like to know that, this is the questions. Now back to the large language model. Is there any resources that I have in my cloud that publicly exposed? Is any of my information or data in a database or a storage layer publicly exposed? In the case of Optus or Medibank, that's exactly the same things that happened based on the MITRE attack. Now, you as a security analyst or engineer, you want to find out this. So it's not easy task. Let's use a generative AI. So now you'll be able to ask, is there any storage layer in my cloud configuration that allows anyone from internet get access to my sensitive data? This is your question as a security analyst. To ask this, you need MITRE attack as a knowledge base, all of this structure in your graph, in your knowledge graph. You need all of your component of cloud listed through the graph, not through the relational database. For example, in terms of Google Cloud, you have Google Storage, you have Google Functions, you have gateways, you have applications. In AWS, you have S3, you have your storage, you have Lambda function as the serverless functions, you have gateway, you have DynamoDB as like a highly available database. These are assets, and each asset has some sort of configurations. Now think about that. Assets are like a node in a database. Configuration is like a properties of that assets. So now S3 storage, not specific about any vendors. Storage as a node has lots of properties, which are the configurations. One of them is publicly accessible. You set it as false. But the problem is maybe that storage has someone as like an admin, as an identity, by the definition has access to this. And that admin is working through the virtual machine. And that virtual machine has access through a public IP. So it means that someone can go through public IP to this machine, which is the initial access based on a MITRE attack, and get kind of like a, based on sort of a triggers, get the identity from this person or this principles, whatever is that, go through this. Now think about the generative AI. If you ask about the generative AI, so it has all of those underlying knowledge base, so that's why I understand the relationship. But again, back to the questions, is there any kind of like a storage that's accessible through the internet? If you ask this one, instead of this, you're saying that, is there any port 22 that allows someone to go through S3? If you ask this, maybe a large language model doesn't understand about what does port 22? What does S3? But if you ask, is there any storage that's accessible through internet, you understand this, but doesn't understand the first one. That's why the prompt, that part through the Generative AI Studio is where that you as an organizations, you're required to write your own prompt, literally add another augmentation on top of your generative AI to teach the generative AI if someone asks about this and this and this means storage. But definitely you don't need to write each. You have, for example, AWS documentation. You can push all the AWS documentation through the prompt in Generative AI Studio and then add that one as another kind of like a standardization through the vectorizations and be able to understand the questions. Pretty much that's the examples about this. So hope this gives enough kind of like a visibility about why knowledge graph and graph database is really important. Even say that is mandatory and necessary for next generation of the generative AI, and why technology like Vertex AI, Google Generative AI Studio helping to even one level enhancing and enriching through the standardization of language input. That's pretty much the entire things that I just wanted to bring. It's mainly around just saying that graph is things that literally going to the underlying of all of those generative AI technology, because AI pretty much means finding the patterns and relationship. It's all about this. Thanks for this. And there are a couple of slides that I'm just putting here. For those who are interested in graph and AI, in 2 months, we have a meetup on graph and AI. Also, there is an academy by Neo4j that there are lots of free courses and self-paced training. You'll be able to have an access or all the way go through the certification professional services by Neo4j around graph technology, and specifically for large language model and generative AI, there are a few courses coming soon. In 3 months, there is a conference. It's free for everyone to register. It's interesting, it's a 24 hours conference because it's around the globe, started from Australia all the way to US, and it's 24 hours. Anytime that you jump on this, you'll be able to see a parallel session, and a few of the sessions are including a training. And if you're interested for next meetup, anything around related to generative AI and graph, definitely jump on this and submit your talk. Yeah, that's pretty much it. Thanks.
You hold on to this. We'll do
Sure. Oh yeah, sure.
Thanks, Payam, for a very informative talk. Looking at the time, we have time for 3 questions, so open for questions.
Yes. Yeah. Sorry.
Hello.
Hi.
What is the difference between the graph and vector database?
Graph vector database. A graph database and a vector database.
Yeah.
Yeah. Sure. Graph database literally is a technology for storage that project whatever is underlying your storage data, because a storage data is file. Even a row and column database, like a SQL service, is files there. So project the files into memory as the connections. This is graph database and allows you to search with that Cypher query through this. Vector database is again another storage layer that store information or series of information as token. And those tokens literally again is become like a file and save on the disk, on the memory. But there are lots of other technology by different companies that coming with another storage layer of token, how we be able to search token more efficiently. Pretty much vector database is storing a tokenized version of information on memory on disk. But there are lots of layers to make it even more efficient in terms of find and search. No worries.
Hi, thanks for the talk. I am very interested in that flow that you put up in terms of this search for the information and then use LLM. I think it's quite clear that the graph database can be quite efficient in getting the right data that you need. But then when you think about actually producing that database, so it seems much easier to create chunked vector embeddings. Just run probably a few lines of code and you actually get that vector. Whereas to construct the graph database feels a lot harder, especially if you're, let's say, a layperson who has to construct it. So I wonder if you could comment on that, if there's actually a huge difference there in terms of constructing the graph database that is useful, or whether there are tools to do that, or if there's a meaningful difference there.
No, that's a really good point. Again, this is pretty much like a trade-off. Graph database, query of the graph is really fast. But why is fast? Because you are putting a lots of memory backend. So literally, if you search through the website that gives you the hotel or flights, that you can search a flight between any cities and you can find across hundreds of the airline gives you the best option. That's a graph database backend. So it's very quick because they put all the information in terabytes of memory. It's a trade-off. You're right. So constructing graph is it's not computationally expensive. Is memory expensive. It's not easy. It requires a lot of computations. There are lots of tools that, based on those who are familiar with the concept of Bayesian statistics, it look at to the pattern or trend of the construction in the past and make a new construction a bit more efficient, similar to neural network training they call gradient descent, that by some experimentations make the graph construct less heuristic. But yeah, back to a point, it's pretty right. It's more accurate and more informative, but computationally is really expensive. It's trade-off between accuracy and computation or efficiency.
Last question.
Hi, this is more about the usage of the thing you just showed, the Vertex AI, I think. This is actually more of a personal use. So like this problem has always concerned me that whenever I'm using ChatGPT, it's always it only has memory for that single session. I'm thinking about if it's possible for me personally to put everything that I want this data model to know about me and put everything I wanted to know about me into that prompt, and so that it will come out of it this new model that can answer all the questions like like any organizations will do. So is that doable or that expensive? And yeah, that's the question.
Yeah. So if I'm understanding your question correctly, because you asked about the like a single ask questions, is it about a memory? So like a long-term, short-term sort of a memories? Because if you're asking a questions through a prompt, it's searched through the database, a lookup, a large language model generating back to you. Maybe you come up with a follow-up question back to this. That's not an easy task for that if you want to build it as a personal project, because that pretty much require a few different layers that is pretty much store your previous questions and answer as a new vector and push it into the database. A new question that you are asking, it goes through a step question. Is it a follow-up questions? A checkup based on the vectors, and yeah, that's a follow-up question. Which question is related, and bring those question into the new vectors. I think that's really complicated solution. Less likely be able to build simply on personal use. The GPT now supports this, definitely, if you're asking, yeah.
All right, thank you.
All right, thanks everyone.
Great. Thanks, Payam.